Yeah, hi everyone, and welcome to chapter 5 on pre-training large language models. So, in this chapter, we are going to finally put together all the building blocks we worked on so hard in the previous chapters. That means the data loading from chapter 2, the multi-hit attention mechanism from chapter 3, but then also, of course, most importantly, the GPT model architecture from chapter 4. So, here we are going to put them together to pre-train this GPT model that we just implemented in chapter 4. And we will do this step by step. So first, we will be implementing the evaluation of generative text models. And then, that will help us to measure how good the text is that the model generates and how we can optimize this. But in order to measure how good generated text is, we have to actually get the model to generate text in the first place. So in this first section, I want to briefly go over again how we use the GPT model that we have just implemented in chapter 4 to generate text. So let me see if I have some nice figures here. So in the previous chapter, in chapter 4, at the end of it, we discussed briefly how GPT models generate text, and that is one token at a time. So if we have an input context, we generate the next token, and the next token gets then concatenated with the input to generate then the next token and so forth. So it's like an iterative process. And then what we talked about was this figure, which looked a bit complicated at first, but I hope it was not too complicated in the end once we implemented it. So what we are seeing here is that we have a number of input tokens. They get converted into token IDs. Then they go through the GPT model and we get out a tensor consisting of 4 rows. So each row corresponds to one of the input tokens. We take the last row, we get the probabilities for each position here, where the positions correspond to the number of entries in the vocabulary. And then we extract the largest position here, which corresponds to the token ID that we want to generate. And we convert this token ID back into text and then have the generated input text. So in this case, it's only one token we generated. Now, going to chapter 5, I won't go over all these here, but where we are, maybe in the big picture sense, we are now finally implementing the pre-training, and it's done in several steps. So there are 7 steps to it. And by the way, maybe before I continue with the text generation, I wanted to say we are pre-training this model here, and later on we will also be loading pre-trained weights from the OpenAI GPT model. So everything we do now is for educational purposes, the training and everything, and then we will also load the pre-trained model. But anyways, continuing with what I just talked about, the generating of token IDs or generating of tokens. So here the figure is very similar to the figure we just looked at in chapter 4. It's just visually a bit differently laid out. And so again, what you are seeing here is some input text for input tokens 1, 2, 3, 4. We will implement a function called text to token IDs, which will take this text and convert it into token IDs. And this is exactly what we have seen in chapter 4. These token IDs go into the GPT model, and the GPT model creates this output tensor consisting of 4 rows, similar to before. And then we will have a code that converts these tensors into token IDs, and then we will have a function called token IDs to text, which will then convert the token IDs back into text. And what you're seeing here is just like a different visualization of what you've seen in the previous figure in chapter 4. It's just a bit more compact, and the focus is here on these 2 functions, text to token IDs and token IDs to text, that we will implement just to make our life easier when we are implementing the training function, so that we can use it in between to print out some results and see what the model is generating to get an idea if it's actually generating useful text or not. So with that, let's maybe get started and just get coding, because I think then these things will become more clear. And what I like to do is, when I start a new coding notebook, I like to import the libraries that I'm going to use in this notebook at the top, because then, for example, in a few months when I revisit this notebook, or maybe next year, or if you are revisiting this, you see exactly what software libraries I've used. And if you have a bug or anything, or things look different, one good place to start is to make sure you have similar libraries installed, because sometimes libraries get updated and they change functions and things might break. In this case, these libraries are all very mature. They don't change much at all anymore. So technically, you don't need to have these exact versions. Let me just print this out. So matplotlib is just a library for plotting the graphs later when we plot the loss functions to make sure the model trains well. So for now, it's a simple, or not as simple, it's a very sophisticated, but it's a basic way of just making plots in this lecture. NumPy is array library that is used by PyTorch and TensorFlow. TickToken is our tokenizer from chapter 2. Yeah, PyTorch, we don't need to talk much about PyTorch because we have used it now so much that I think it should be clear. And by the way, I'm using PyTorch 2.6, but when I started writing the book about 1 to 2 years ago, it was PyTorch 2.0. I tested all the code on 2.0, 2.1, 3, 2, 3, 4, 5, 6. It works all the same. So, it doesn't really matter which PyTorch version you're using. Older ones are also fine. With TensorFlow, that's interesting though. You don't have to have this exact version, but you need to have a version of TensorFlow. Why? I mean, this book is not using really TensorFlow. We are implementing everything in PyTorch here. But so I mentioned briefly when I scrolled through the figures here that we are going to load pre-trained weights from OpenAI. And back then, when OpenAI generated the GPT-2 model, they used TensorFlow. Now, TensorFlow is not very popular anymore. I mean, not at least as popular as PyTorch anymore. It's also not super actively maintained, in my opinion, because it took a long time, for example, to even get NumPy 2.0 support in TensorFlow. And I know that not a lot, but a few readers had issues with TensorFlow on Windows. It's not everyone. It's, some people had some incompatibility, so I don't know exactly why. But I feel like, TensorFlow is sometimes a bit tricky. So right now, if you get an issue with TensorFlow here, I would say don't worry about it yet. We don't need it yet. We will need it only at the very end of this code notebook. So you can, continue and maybe revisit this later. So it will be just at the very end when we are loading the weights, because we only use TensorFlow here to briefly open the weight files that OpenAI shared. And then we will convert these weights into PyTorch. But for this intermediate step, for just opening the files, we will briefly need TensorFlow. But even then, in case you can't get it to work, if you go to my GitHub repository for the book, I do have a bonus section for chapter 5, where I also implemented it with the Hugging Face Model Hub, where you can also load the weights with different libraries. So there are some alternative weight loading strategies here I've outlined. And the reason why I'm not using those in the book is these are not the official ones by OpenAI. So I preferred using the official ones that OpenAI shared, the official weights, and they happen to be in TensorFlow. But this is a good backup solution in case your computer doesn't support TensorFlow for some reason. But let's cross this bridge later when we get to the section on weight loading. For now, maybe if this doesn't work, just comment it out or something like that. So then to continue, another thing is we had this, there we go, this configuration file here. So this is from the previous chapter. I will make some small modifications. I will change this to 256 because I'm running the code here on an old MacBook Mini. Old MacBook Air from 2020, which is not very powerful. And it has limited memory, compute memory. And the longer the context size, the more compute memory you need. And so I'm just making it compatible to my computer here. Chances are you have a newer computer where it's just fine, you have more RAM, maybe even you have a GPU. So the code we will run later will also optionally run on GPUs. But just to make it compatible to most people's computers, I thought erring on the lower end might be a better idea, so you don't get any issues, but feel free to also try out larger numbers. And that's basically the small modification I'm making here. And then we are going to implement our GPT model. So for that, we do from previous chapters, import GPT model. And I should say, in order for that to work, you need to have a file here called previous chapters. And so here it's just a file I created. What I put in here is all the code from chapter 2, the data loading code, the dataset class and the function to create the data loaders. Then the multi-head attention mechanism from chapter 3 that is used for the GPT model. The building blocks, the placeholders we replaced with the actual functions, the layer norm, the GELU activation, feed forward module, the transformer block and everything that goes into the GPT model. So that's the main thing here, and this GPT model depends on the other ones. So that's why everything is in here. And I also added this generate text simple function from the end of chapter 4. So this is all the previous code. I just put it together into this file here because then we can import. So here, this will import the GPT model from this file. So yeah, just make sure you have it here. And then we are going to use the model, so torch manual seed, so that we both, you and I, get the same results. And then the model itself. So we will, there we go. We will use this dictionary file. And then one thing I forgot actually in chapter 4, sorry about that, the evaluation mode for generating text. So eval, what it will do is it will kind of disable all the random elements in a model. And in chapter 4, we talked, I think it was chapter 3 actually. In chapter 3, we talked about dropout. So dropout is a random dropping of nodes during training to prevent or reduce overfitting. But we don't want this random behavior during inference when we generate text. So we want to disable it here. So that's what we're doing. We're disabling dropout so that there is no random dropping during inference. We only need it during training. Now, this one, eval, probably stands for evaluation or something, but it will just, it's like, you think of it as an inference mode or prediction mode or something like that, where we don't want randomness. So that's what's happening here. The reason why I'm using the semicolon is I should, of course, import PyTorch. For this one, we need PyTorch because I'm calling torch.manual. So if I don't do the semicolon here, you will see it prints the model architecture, which is quite nice. You can see what the model looks like, but it is also creating a lot of clutter here, which is why I'm adding the semicolon. And by the way, if you want to make the model ready for training, we will do that later. The opposite of eval is train. So that's the opposite. So to make it trainable again. Okay. So that is the model itself. Now let's get to the functions. So let's do this one by one. We use tick token as our tokenizer. And then from previous chapters, we implement the generate text simple function. What we do is we have the text as input to our text to token IDs, the tokenizer itself, and then we use the tokenizer to encode text. So that's what we're doing here. Here we're adding a batch dimension because our model was implemented to work on a batch, not on a single Python list or tensor. So here that's what we're doing. Nothing too special. Let me actually initialize the tokenizer and give some text to the function just to make sure it works. So let's try this actually out in practice. So we do start context and then tokenizer. Let's see. So yeah, it's converting correctly text to token IDs. Now we implement the opposite. So what we do is we will implement the token IDs to text. And here it will receive the token IDs that we just generated as input. So let's maybe save them here. And it will remove the batch dimension because then we can convert it into a list because the tokenizer itself works with Python lists. And by the way, this is exactly what we have done at the end of chapter 4 here when I did the squeeze to list and everything. So this is the exact same thing we're doing here. So the squeeze to list essentially. I'm just packaging this in a function so we can reuse that without having to type it every time. And then a tokenizer. Okay, so yeah, we converted the tokens back into text, and these are our convenience functions. Yeah, the main part is essentially setting up these functions, and then we can also use the generate text simple function, which we implemented also at the end of chapter 4. That's from the previous chapters, or we have it also here in chapter 4. And with that one, we are here using our text to token IDs to create the token IDs. We say how many token IDs we want to generate, and then yeah, the maximum context size of the LLM. So let's run this and let's take a look at the token IDs. So we can see this should be 14. So it's a double list, so I can actually squeeze that to make it a single list here, and then I can also just do shape. It doesn't matter. So we see we have 14 token IDs, and the number 14 comes from the fact that we have 4 input IDs, 1, 2, 3, 4, and then we generate 10 new IDs. And now we can then use our text to token, token IDs to text function to convert these token IDs back into text. So let's see what happens. It's missing the tokenizer, of course. So what happens is, yeah, we can see the first 4 tokens are indeed correct, that these are the ones that we provided, of course, but then everything else doesn't really make sense. So we can see it's, gibberish. So what happened here? What happened here is that the model, we initialized it with random seed, we haven't trained the model. So if we want the model to generate coherent text, we have to show it how, and that is essentially the training. But before we do the training, we still need to kind of have a numeric way of visualizing it, because right now we as humans, we look at this and say, oh, this doesn't make sense. But how do we actually quantify this? How do we measure how good this is, right? So because we need a measure of this in order to optimize this measure. So in the next videos, we will see how we measure the quality of this generated text. So in the previous section, we had the GPT model generate text, and then we as humans, we looked at the text and we saw, oh, this is actually not very good text. So in this section, we are now going to implement a way we can measure this quality of the text more numerically. And so for this, we are going to calculate the text generation loss. So loss function is a measure, in this case, how good the generated text is. And then we will be using that to optimize, or more precisely to minimize the loss, to optimize the generated text later in this chapter. For now, we are implementing the loss itself, how we measure this. And yeah, the technical term in this case for the LLM training of the loss function is the cross-entropy loss. So cross-entropy loss is a loss function that helps us measure the quality of the generated text. And we will also briefly talk about a related measure, the perplexity of a text. You might have heard perplexity before. We will also briefly talk about how perplexity is related to cross-entropy. But yeah, we will tackle this one step at a time. So just to briefly go back to a figure that I showed you in chapter 4, at the end of chapter 4, we had this figure where we went from token IDs to these tensors. And then we computed the logits and the probabilities of the last tensor. And so this was essentially for generating the next token. Now, what we are interested in is not just generating the next token, we are interested in measuring the quality of each generated token. So what we are now analyzing is this whole thing, because for each input token, then LLM generates a vector, and this vector contains information about the following token. So remember in chapter 2, we set up the inputs and the targets, where the targets were shifted by 1. So we had, if we have something like hello, I am as our inputs, the targets would be comma, I am a, right? So then the output here, this comes from the first token, this should be able to generate the comma token. Maybe if this is too complicated, let me show you a simpler example. So let me maybe give you a concrete example where we have inputs and targets. So what I'm trying to say is if we have token IDs corresponding to some input text, for example, every effort moves, if we convert this into tokens, we will get these tokens here. This is using the tokenizer. And the targets, so here we have the corresponding targets, are shifted by one position. So this would be effort moves, and then the next token we want to generate. So we have this shifting by one position, similar to what we have done in chapter 2. Okay, so, and we want to know if the model generates tokens, we want to now measure how good are those for predicting this next token. So we'll get there maybe one step at a time. So here I'm showing you one input and then the targets. This is what we want the model to generate. Here we have a second input, just so that we have multiple examples. And here the second input is I really like, and then the targets for that one would be, for example, really like chocolate. So really like, so because it's shifted by one position. Also, I chose these examples so that this one has nothing to do with this one, because I want to highlight when we have a batch of multiple inputs, these rows are unrelated to each other. So the relationship is between the first row here and the first row here, and then the second row here and the second row here. Because the inputs correspond to the targets, but there doesn't need to be a relation between the first and the second example here. If you are pre-training, you could, for example, chop up your text with a sliding window approach that we've done in chapter 2. In that case, they kind of relate to each other, but it's not necessary. They can be totally independent, like shown here. Now let's generate the logits. So what we're doing now is we are generating these outputs here, the logits. I can also maybe just show you the figure we looked at earlier in the previous section here. So what we have is the input text into tokens, and then we generate this output tensor, these logits. So let's do that. So here, similar to what we have done before, we generate the logits. And let's just take a look at the shape of these logits. So what we see here is it's 2 by 3 by 50,257. Where does this number come from? So 2, because we have in the inputs 2 rows. Each row has 3 tokens. So that's where the 3 comes from. And each of the logits is a 50,257 dimensional vector that corresponds to the vocabulary size. And then we had the step where we converted these into these probability tensors. We had the softmax function on the logits, like this. And this one, let's just take a look at the shape. And this one has the same dimension here. We haven't extracted the last tensor or anything like that. For this one, we're looking at every tensor now. So so maybe to see this more clearly, I should have a figure somewhere here. So we have an input here. Every effort moves, which we convert into token IDs. I'm using a different vocabulary here. I'm not using the 50,257, so that allows me to fit it into one slide, because 50,000 would be quite long. So we have these token IDs we get from some input text. And then each token ID is converted into the logits and then the softmax, the probabilities. So here you can think of this row here as what we have here. So if I maybe show it to you here. So we have 2 input examples, so this one and this one. Each one consists of 3 rows, 1, 2, 3. And each row here is, so it's kind of wrapped around the line, but this is, you can see it's dotted out, it's 50,000 dimensions. So instead of looking at 50,000, because it's very long and then we had to dot out these lines, I'm using a smaller vocabulary so that everything fits into one line. And one thing about the softmax function, if you recall, these sum up to 1. So what we're looking at here, the vocabulary 0, 1, 2, 3, 4, 5, 6. So we have 7 entries. So there should be 7 entries here, 7 probability scores. And the first value tells me for this token in the input, I have a 10% probability to generate A. I have a 60% probability to generate effort. I have a 20% probability to generate every. I have a 5% probability to generate forward and so forth. So these give me the probabilities of the next token that is likely. How probable is this that this is the next token? And so the model learns during the training later to give high probabilities for the true token that we want to generate. The true token or the target token is what we have in our targets. So you can see every effort moves you. These are our targets. These are our inputs. We want the model to generate the targets, so the shifting by one position. So here in this case, we want a high probability for the target. And the target effort, so if I go back here, we had the inputs, every effort moves, and the targets. Now I want for every, I want a high probability for effort. And I want for effort, I want a high probability for moves because it's shifted by one position. So here I want a high probability here. We have a 60%, it's the highest probability. If I look up the index position, so 0, 1, 2, 3, 4, 5, 6, 0, 1. So this is index position 1, and this corresponds to effort. This is good. This is what we want. Now, next, for the second token, I look up again the position. What is the highest probability? Oh, it's this one, 35%. It's the highest one. It corresponds to token, so index 4, token ID 4. What is token ID 4 in my vocabulary here? 4. 4 corresponds to moves. So I have this inverse vocabulary. You can see this is like flipped and it's easier to look up. So 4 corresponds to moves. So I generate moves. Next, moves as my input token. I look at my probability tensor. Where's the highest probability? Oh, here. What is this? Oh, index position 5. 5 corresponds to U. Okay, I generate U. And this is how we go from probability scores back into these here. And if you recall from the previous chapter 4 video, when we implemented the generate text simple function, we used the argmax to determine this index position. It maybe looks like a highly complicated figure, but all that there is happening here is we have a vocabulary where we go from token IDs to, so from tokens to token IDs, we get the softmax, and then we go with the argmax backwards from probabilities to token IDs and then back to text. Okay, so it was a lot of information maybe, hopefully not too complicated. Now we have these probas here. The probas, short for probabilities, are these values here, these rows you can see. They're just a bit bigger because we have this 50,257 dimensional vocabulary instead of having just 7, right? So yeah, that is what we have so far. Now, let me show you the code to convert this back. So here, argmax, like I mentioned before, argmax is going from probabilities to these indices. So these indices, I'm just showing them here twice, it's just the highest position of the position of the highest probability in each of the cases. So this gives me the token IDs of the highest probabilities. So for the first token, it's 16,000 in the vocabulary and so forth. These numbers are higher because, like I mentioned before, this is a smaller vocabulary for illustration purposes. Okay, next, so we have these token IDs. Next, we can convert these token IDs into text, similar to what we have done before. And so here I'm indexing, just looking at the first one, the first example. So we have 2 examples in text, 0 and 1. For simplicity, I'm just looking at one of them here. So you can see I'm just looking up target 0. I'm just looking up this here. Every effort moves you. It's just a lookup. And now I'm looking up what has our model generated for these targets. If I'm going through this one, ideally what we want is that the generated outputs match the actual targets. So ideally, we want the model to generate this. But when I'm looking at the result, it writes something like ARM T Netflix, which does not make any sense. And this is because we haven't trained the model yet. After the model training, ideally the model will generate this text as similar to the targets, basically. Okay, so this is where we are so far. Next, here I'm just focusing on the first example, similar to here, just assigning it 0. Why? Just to keep it simple, that we don't look like that we don't mix them up. So let's just blend this out for now. We can focus on this later. And so what I'm looking at here is the probabilities for the first example. And then I'm looking at these 3 tokens. So we have 3 tokens in the input, 0, 1, 3. And similarly, I look up the corresponding targets for that one. So here, what you can see now, when I said targets, I'm meaning the IDs. So for each of the 3 token positions, I'm getting the target indices. So I'm looking up, maybe one step back here. So here I'm looking up the highest probabilities because that is what we are generating. Now what I'm looking up is what should be, what are the positions of the target IDs. So here it's the same. So the highest position is the position of the target ID, because the target ID is happens to be every effort moves you if a model generates the correct thing. So we have 1, 4, and 5 as the correct target IDs in this case, and they correspond to the highest positions. But what if, I unfortunately don't have a figure on this, but what if our model is not correct, right? So I'm looking up in this first vector, what is the target ID 3626 for the first row? What is the probability in this one for this position, right? Because that is the one that we want to maximize. So I'm looking up in this first row, what is the token ID 3626? And then I'm doing the same thing for 6100. I'm looking up where is, or what is the probability corresponding to position 6100. And then in the last one, 345, what is the probability at position 345 in this whole vector here? And so that's what I'm extracting. So all of them are very small numbers. They are very close to 0. That's because the model is not trained yet and because we have a very large vocabulary. And in our ideal case, what we want to do is we want to increase those ideally to be close to, let's say, something like 90%. And that happens during training, so that the model learns to associate the generated probabilities corresponding to the text targets to be very large values. Now they're very small, but we want to make them very large. Here we can do the same thing for the second text. So again, very small values, and we want to make them very large, basically. And so in order to make them large, we have to measure this numerically, how good this is, basically. So for that, it's a multi-step procedure. So we first compute the logarithm of all token probabilities, and I can share this later. I have a whole lecture on why log probabilities. It will make it a bit simpler during optimization. There's something called maximum likelihood. If you've never heard of this, maybe don't worry about it. I will just do it more conceptually here, but optionally I can share a lecture on it. The idea is essentially that we turn the multiplication into a sum in the maximum likelihood, but different topic maybe for a statistics lecture. Here, so just think of it maybe for numerical stability, or maybe I can just show it to you if you are curious. And so it's not the right one. So if you go to my website, sorry, browser autocomplete here. If you go to my website under more, I should have courses here where I taught a statistics class back in the day when I was a professor here. And I should have this whole lecture here on multinomial logistic regression and softmax regression, where I go over all these things more slowly and computing the cross entropy and so forth. So for here, maybe just think of it as a thing to make it numerically more stable. So we are computing the log probabilities. We are taking the log, and what we are doing is we are taking, so we are first concatenating those two, because here they are separate, but we want to concatenate them, so to have them all in one, because then it's easier to apply the same computation. We don't have to apply it separately to two different tensors and so forth. So we're just combining it into one tensor. And then we apply the log. So here, so we turn this from very small values into now these negative values. So the smaller the value, the more, the higher the negative number here is, for example. So that's what we're doing here. And then we can compute the average. So we can do torch dot mean. Oops. And yeah, we provide the log probas as input. And you can see we get a value of minus 10.79. So that's the average log probability. And then what we could do is we can multiply this by -1 to get a positive number. And this is, so it took us a long way to get here, but this is the so-called cross-entropy loss. And during training, our goal is to make this close to 0. That's our goal, basically. We want to get this number very close to 0. And if this number is close to 0, that means these values are close to 0, which means that these values are, so the log varies is the same. Let me get rid of this, it's less confusing. So again, so we want this to be close to 0, which means that these are basically very close to 0, which then means that these are very large values, because when you look at this, let's do a torch.log, let's do 0.99. You can see this is a number that is close to 0, basically. So our goal is essentially to make the probabilities very large. So ideally 1, which will make those close to 0. And if we have a very small probability, this will be a very, 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 very negative number, like minus, I don't know, minus a very large number. So here, minus 36, for example, here. Yeah, so our goal is essentially to get those close to 0, which means that the probability will be close to 1. Because if this is close to 1, this will be corresponding to the correct target ID. Because again, right now we got the target ID, the probability corresponding to the target ID. We want to make it large to make sure it gets selected by the torch argmax. So we want to make sure we have the large values at the right position in each case here. Okay, so, and this is where this cross entropy comes from. Again, like I mentioned before, if you want more nitty-gritty detail, you are free to watch these videos. It's a lot of videos here, I think. But it's not really necessary, to be honest. I think all you need to understand is that we are just measuring how good our generated outputs are, and we want to get this number close to 0. Now, this is also a lot of steps, right? So we have quite a few steps with a softmax here. So first the logits, then the softmax, then the argmax, and then the log, and then the -1. And there is a quicker way in PyTorch, and there is actually this torch.nn.functional.cross entropy function. Maybe I have a figure on this. Let me scroll down. one moment here. So what we have done so far is we went from the logits to probabilities to get the probabilities corresponding to the target token IDs. We converted them to log probabilities. Then we computed the average, and then we computed the negative log probability. So just in a more cleaner layout, these are the steps. And you can see that's the same number we got. We applied these different steps one at a time to get the cross-entropy loss. So the cross-entropy loss is a synonym for negative average log probability. It depends a bit on where you come from. Like if you are a statistician, you would probably say negative average log probability. If you are a computer scientist who studied information theory, you would probably say cross-entropy. So cross-entropy is just a different word for this negative average log probability. It just happened that both fields independently discovered this measure or derived this measure. And in PyTorch, this is called cross-entropy because it's more computer sciencey, deep learning, machine learning package. In PyTorch, we can also compute this. So there's one trick though in PyTorch. So in PyTorch, it works with the logits directly. So we have to first flatten our logits. So our logits have shape 2, 3, 50,257. And so we have to flatten those to combine those dimensions because the logits are expected, in our case, to be 2D tensors. So we do logits.flatten 0, 1. Let's call them logits flat maybe. And then logits flat.shape. And so we see we combined those dimensions. We just concatenated along this axis. And so we have now the 6 times 50,257 dimensional tensor. And so we can pass these logits flats and then the targets. So for the targets, we have to do the same thing. So for the targets, if I look at the shape, we have the 2 by 3, similar to how we combined the dimensions here to 6. We do it here too. So we do flatten. I think I just need one because there's only 2 dimensions. Let's double check. Yeah, so we combined those targets flat. And so here, what this is doing internally for the logits, it's internally computing the softmax probabilities. It's getting the correct probabilities according to the target token IDs. So it's getting them from here. That's why we have to provide the targets. And then it's computing the log probabilities, average them, and compute the negative, like the -1. And so it all happens inside here. And it's also optimized. So they have optimized function calls, PyTorch CUDA kernels. When you run this on the GPU, this will be actually faster than our manual implementation here. So let's see if we get the correct results. And you can see, yeah, we have now 10.79, which is exactly what we got before. But before, yeah, we had all these individual steps. Now we have combined it in one step. Okay, and so I hope this is making sense in some way. I know it's a lot of stuff that happens here. At the end of the day, I think all you need to know is that what we want to do is we want to make the probabilities of the positions corresponding to the target IDs as large as possible. So yeah, that is our goal essentially. Our untrained model will not generate anything useful. Our untrained model will generate gibberish, but at the end of the day, we want to train it such that it generates the correct tokens that we provide in the target tensor. So in the next sections, we will be working with this further and try to minimize this loss, which will then correspond to large probabilities in the correct positions. In this section, we are going to talk about calculating the training and validation set losses. So what does that mean? So in the previous section, we talked about the cross-entropy loss, which is a measure of how good the generated text is that our model generated. But in the previous section, we only calculated this for a small sample text. Now we are going to calculate the cross-entropy loss on the whole training and validation set that we are going to generate for the model training. So again, the cross-entropy loss, how it's calculated, it's between the logits, the outputs of the model, and then the target token IDs. So the target token IDs tell us essentially what are the tokens that the model is supposed to generate. And if the target token IDs are associated with a high probability score when we apply the softmax to these logits, which happens internally in the cross-entropy function like we talked about. But what I'm trying to say is ideally we want the model to output high probabilities for those token positions in the vocabulary that are associated with the target token IDs. And only then, if we have these high probabilities, the overall cross-entropy loss will go towards 0. So ideal case, it would be around 0, which means that the model outputs very high probabilities for the correct tokens. So that's our goal. Right now, it's very large. So it's 10.79, which is actually very, very large. So we want to reduce this number towards 0 in the process of the model training. But before we train the model in the next section, we want to first apply this calculation to the training set that we will be using for training the model. And here, specifically, we will be using the same training set that we introduced in chapter 2, the verdict by Edith Wharton. So just to give you the brief overview where we are in this chapter before we get to the code. So we talked a bit about text generation. We computed this cross-entropy loss in the previous section. Now we are applying this cross-entropy loss to the training and validation sets. And then later in the next section, we will be actually training the LLM finally. And then we will talk a bit more about more advanced text generation strategies. So we had a very simple one. I will add some sampling procedures to that one. We will also then, of course, save and load our model because, training might take a long time. So it would be nice if there's a way that we can save the model and load it later so that we don't have to retrain the model every time we want to use it. And then I will also show you how we can load the pre-trained weights from OpenAI into our LLM architecture. But let's talk first about calculating the training and validation set losses. So like I mentioned before, for this we will be using the verdict from chapter 2. And so here it's just boilerplate code which will load the verdict. If it's not already on your in the local folder here, then it will download it from the internet. So here in this case from my GitHub repository. If it is already in a file called the verdict relative in the same folder relative to this notebook, it will just open the file. So there's nothing really interesting here. It's just loading the file. It's never a bad idea to also just double check the data set to make sure it's loaded correctly. If this were a bigger data set, this would be very cluttered and very, very large. So maybe it's also not just a bad idea to only print a few characters. So we can see, this text looks okay. It's loaded correctly. There's no error or anything. So that is our training set. Also just like a sanity check, we can calculate the size of the training set again. So the number of characters in the data set, and also the number of tokens. So here using the tokenizer, the tick token tokenizer that we used before, we can see it's 20,000 characters and 5,145 tokens. So next, what we are going to do now is we are going to divide this into a training subset and a validation subset. So I should have a nice figure on this here. Here. So suppose this is the verdict data set, this whole thing here. And what we want to do is we want to divide the data set into a training portion, here the large box at the top, and a smaller validation portion. So the training portion is what's used to train the model, and the validation portion will be used to evaluate the model during the training, to get a rough idea whether the model is overfitting to the training set or not. But we will get to that when we, implement the training function. For now, maybe just think of it as dividing our data set into two portions. And what we are going to do is we are applying this procedure to each of the portions, of the two portions. I'm only showing it for the top portion, just, because there's not that much space here in this figure. But all these steps, they will be also applied to the validation portion at the bottom. But yeah, looking at one of these portions, in this case, the training portion, what we are doing here is we are subdividing the training set into these little boxes. So the box here has a size of 6. Why 6? That's so I can fit it into this figure. But yeah, if you consider our original setup, we have a context length of 256. So this is the context length, how long each training sample is that the LLM receives. We would make it 256 in our code because, yeah, it's of course better to have larger context sizes to train more efficiently. But here in this case, because the figure gives us limited space, I'm using a batch size, a context length of 6. So you can see the first 6 tokens are contained here. And this is like just a list of the raw tokens. For example, if I go here, let me see. So this should be this list here. It's a very long list. So maybe let's immediately again get rid of it so it's not too cluttered. But yeah, what you are seeing here, this list is essentially this list. And now we are subdividing it into training samples. So the first 6 tokens will be the first training sample. Then the second 6 tokens will be the second training sample, and so forth. So here you can see we organized this in a tensor where we have 6 columns, so 6 tokens per training example, and each row is a training sample. So that's basically what you're looking at here. And then what we are doing is we are subdividing the whole data set here into batches. So here I'm using a batch size of 2. So the first of 2 training samples are in the first batch, 2 training samples are in the second batch, and 2 training samples are in the last batch. And what you can also see if you pay close attention is that the batches are shuffled. So here, for example, you can see that the first row does not correspond to the first row here. It's like the 4th row or something like that. So because we use shuffling in our data loader, like I explained in chapter 2. And yeah, and this is the pipeline for going from text into a data loader implementation to obtaining these batches that we will use for the training. And we will also use the batches to evaluate our model, because it would be very expensive to pass the whole data set all at once into the model. So we will be evaluating the model by iterating also over these batches. But maybe this will become more clear once we implemented this. So the next step would be loading just a data loader that we implemented in chapter 2. So here I have my previous chapters file where I have all the different functions and methods and classes we implemented in the previous chapters. And one of them was in chapter 2, the create data loader version 1 file or function. And so I'm loading it here. We'll be using it in a few moments. Then I'm saying, okay, we will use 90% of the data for training, and then the remaining 10% will be used for the validation. So what you're seeing here is, I need to make this more clear. What you're seeing here is the number of characters that make up the first 90% of the data set. So if we have, let's say 0.9, then this is the number of characters that we see up here. So if I execute this, you can see the first 18,431 data points will be the training data set. So if I have text data here, what will happen is that this will be our training data set, and then the remaining tokens or characters from 18,000 till the end will be our validation data. And so that is what you are seeing here. So that's all that's happening here essentially. So we have now a training set and a validation set. And next, we are going to initialize the data loaders. So let me just copy it here so I'm not making any typos. And this is the same that we had in chapter 2. So we have the training set and the validation set. So we have two data loaders. And we use a batch size of 2, similar to the figure, the context length, and the stride. And so if we would set that to 6, it would look like here, right, where we have context size of 6, and then we have a stride of 6, which means moving 6 positions over and getting the next 6 and so forth. Except in our case, this is a hyperparameter that we have set to 256 up here. Yeah, and then we drop the last batch if the number of the data set size is not evenly divisible by the number of batches. And then we set the shuffling, and that's essentially it. So there's nothing really new compared to what we have covered in chapter 2. Yeah, and then what I usually like to do is I like to iterate over the data set. So if you have a very large data set, I would probably do it like this. And so this will just make sure that there are no errors in the dataset, where it iterates smoothly through the dataset. And you can see the first tensor here is the training set tensor, and this is so the input IDs, and this is the target IDs. That's the way we set up our data loader. If we go back here to the dataset, you can see we have the input IDs and the target IDs. And so this looks good. So we have a batch size of 256 tokens each. If you want to, you can also, because it's a relatively small data set, you can just iterate through all of them. And so we see how many batches we have. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 batches. Then what we can do is we can do the same thing for the validation set. We can see we only have one small validation set. So that's like really, very, very small data set, so that the training doesn't take forever. Remember, this book is for educational purposes, and we will be loading the OpenAI weights also later on, so you have a more capable LLM. Here, it's really just more for illustration purposes. I wanted to print a few more statistics here. And so what I'm doing is, remember this number of elements method, which computes the number of elements, the number of tokens in each of these, right? So if we have x.shape, we have 2 times 256 tokens. So we can compute this as follows. So this is the number of tokens. So here I'm just computing brute force the training tokens we have in our data set by iterating through it. And I'm doing the same thing for the validation set. So let's print the number of training tokens and the validation tokens and add them up and see if we get roughly what we have up here. So just to make sure that, the numbers still make sense. It's a good way of sanity checking. So what we can see here is that we have 4,608 training tokens and 512 validation tokens. This looks okay, of course, compared to what we have computed before, but this one is a bit suspicious. So when we add up the training tokens and validation tokens, why don't we get the 5,145 we had earlier here? And so there are 2 reasons. So the first one is, if we look at this figure again, what we are doing is we are subdividing the dataset into these context length long chunks. But then if this dataset is not evenly divisible by the context length that we define, there will be a leftover chunk at the end that doesn't really fit this. So if we drop this, then of course we will not have so we will have dropped some of the tokens, the last, in this case, 25 tokens, because they're not divisible by the 256. And the other one is also when we consider the training loader and we drop the last one, if the last one, or if the number of batches is not evenly divisible by the batch size. But yeah, so that is why we are losing some tokens here, but it's not a bad thing. We want to really make sure each batch has the same size so that we don't have any weird loss spikes during the training. And in reality, when we're training deep neural network, we have trillions of tokens usually, so it doesn't really matter if there are a few tokens missing. It really, really doesn't matter at all. We have so much training data, this is just like a drop in the bucket. Okay, so this looks good then. So we have 5,120. Now, the goal of this section was to compute the loss of the training set, or the loss on the training set and the validation set. So how are we going to do that? So I have a few functions here, two functions. They look a bit complicated, but if we go through them in a, I would say, strategic manner, then I think it should hopefully make sense. So maybe starting with this calculate loss batch function. So this one is, I will get to the details later, but this on a high level is a function that computes the loss on one of these batches. So here we are iterating over the training order, and we get the input batch and target batch for each iteration. So this is one input batch and one target batch in our training order. Essentially what we are returning here, right? Okay, so this is computing the loss on one batch, the calc loss batch function, and the calc loss loader function will apply this calc loss batch on each of these batches in an iterative fashion. So it will iterate over the data loader. That's essentially what's happening. So, and in each calc loss batch function here, what we are going to do is we are computing the cross-entropy loss, similar to what we have discussed in the previous section, between the layer outputs, the logits, and the target batch. So this is exactly what we have done in the previous section, now applied, instead of a prompt, applied to a batch. Now you see this here, this line. What is happening here? So this one is transferring the data to a device. And we have this device here too, which gets passed down here. Now, what it does, it's if we have a model sitting on a certain device, so maybe let me just show you an example. So if we have this line here, for example, this will check. So your computer may have a GPU, a CUDA GPU. So a CUDA GPU is a GPU by NVIDIA that supports the CUDA library. And CUDA is, you can think of it as a programming language like C++ for NVIDIA GPUs. And if you just execute this one, you can essentially double check whether your computer supports this, if it has a GPU and supports CUDA. In my case, it returns false because I'm running all the code here on a MacBook Air, which is an Apple device, so it doesn't have a GPU, of course. But if you want to, there is an equivalent. It's called MPS. It's called MPS stands for Metal Performance Shaders, I think. It's like an equivalent by Apple for CUDA to utilize the what is it called? Apple Silicon GPU, essentially. So in my case, I have this Metal Performance Shader support. So you could technically replace this, in my case, by this one, and it will be faster than the GPU. Sorry, not the GPU, the CPU. It will be faster than the CPU on this machine. I'm still using the CPU here though, because it's a bit more stable. When I started writing the book, I tested all the code with MPS, CUDA, and CPU, and I got similar results on CUDA and CPU, but I got slightly different results when I used MPS. That was back in PyTorch 2.0. Over the course of the last few months, when they released PyTorch 2.6, I noticed it became a bit more stable. So you can get similar results now with MPS that you could get with CUDA and CPU. But sometimes you get some rounding errors because it's a bit newer, the MPS support. So, but yeah, even though it's slower, just to make sure I get the same numbers you might be getting, I'm using a CPU here. And so what is happening here is that we're transferring the data, the input batch, to the same device where the model is sitting on. So what we might do is we want to, for example, transfer the model to the target device. In our case, this will not do anything because by default, the model already sits on the CPU. But if you're so this is why I like to do the semicolon, by the way, because it outputs the whole architecture. But if your computer supports CUDA, then this will transfer the model to the CUDA device, or if you chose to use MPS to the MPS device. And then we have to make sure, though, that the data is also transferred there, because otherwise you have data sitting in the CPU memory and the model sitting on the GPU memory, and then, yeah, they won't be able to easily communicate. So we have to make sure they sit on the same device, and that's essentially what we're doing here. Here, what we are doing is just some initialization of the loss, because we will be computing the loss in an iterative fashion. So for each batch, we will get the loss added up. So we have the plus equal, so we add it up to the total loss, and then we divide by the number of batches. It's just like an iterative way we compute the loss, and then just some baseline checks. If there's no batch in the data loader, then it will just generate a not a number. Yeah, and otherwise we can define the number of batches here. So for example, to make computing cheaper, if we have a large data set, we only want to test something, we can enter 2, then we'll only compute the loss over 2 batches. But if we set this to none, it will use all the batches. So length data loader, for example, if we have length train loader, it will give us all the batches here. In this case, we have 9 batches. Yeah, so this is what this the combination of the two functions are doing, and this will then calculate the loss. So let's do it. Let's compute the loss here on the training set and the validation set. So I'm setting the manual seed because there's a shuffling involved, but it shouldn't make a difference actually for this calculation here, because here we are going to iterate over all the batches anyway. If we had a num batches 2, you might get different results because the 2 first batches might be different depending on the random seed. Here, since we iterate over all of them, it doesn't really matter whether we use a random seed or not. Of course, we use our torch no grad, because otherwise we will be constructing this computation graph of the model in the background, and we don't need the computation graph just yet because we're not training the model. So this is just like an efficiency tweak. And then, yeah, we compute the training and validation loss using our calc loss loader function. Let's compute this, and this might take a bit because, yeah, oh, it's actually quite fast because it's iterating over the whole data set and then passes it batch by batch to the model. And we can see the training loss is quite large here. So it's about 10.98. It's approximately the same that we've seen on the sample prompt in the previous chapter. And this is because the model is not trained yet. Ideally, when we train it, we want to get that below 1 at least. So that would be pretty good. And by the way, before we go to the next section, I forgot to introduce the topic of perplexity. So there's a concept of perplexity, and this is just like another measure to measure the quality of the generated text. And you have maybe seen or heard about this before in the context of LLMs. And so the perplexity is measured as the exponential of the loss. So for example, if I have a loss value like this one, I can put it in here, and then the perplexity would be 50,900 something-ish. And so the perplexity tells us how unsure the model is for the number of words. You can think of it as the model in the vocabulary is unsure about that and that many words. So how many words do we have in the tokenizer again? Actually only 50,000. So, you know, it's like a rough estimate. It should actually be around 50,000-ish. So I think if I make this a bit smaller, like you can see how sensitive this is. Yeah, so what it tells us, it's basically the model is unsure about any of the words or most of the words in the vocabulary. So in that sense, our model is not very good. It's not very trained. We have a high loss. We want to get this loss down to around 0 ideally, but realistically, maybe 0.5 would already be good. So it's unsure only about 1.6 words in the vocabulary, for example. So unsure means it doesn't really know at which position what word it generates. At any position, it might take any of the words in the vocabulary as being equally likely as the next word. And this makes sense because we haven't really trained our model yet. So the model doesn't really know what it should generate as the next token. So that is going to be the task of the next section, where we will be implementing the training function to teach the model to be more confident about generating the next token. After all this hard work in the previous chapters, that means implementing the data loader in chapter 2, implementing the attention mechanism in chapter 3, and then implementing the GPT architecture in chapter 4, we are now finally ready to train the LLM. We have waited so long for this, but yeah, finally we reached the section on training the LLM using the cross-entropy loss that we have introduced earlier in this chapter. So let's go through this step by step. I will introduce you to the main training pipeline first. So here is a figure that will conceptually explain what's going on before we dive into the code. So what we do is we iterate over the training set multiple times. So that is called a epoch. So one iteration over the training set is called one epoch. So that means if we're going through the verdict data set one time, that's one epoch. We could do it multiple times. That would be then multiple epochs. So it's a for loop. And then inside each epoch, we iterate over the batches. So this is essentially the iteration over the training loader that we've just seen in the previous section. What we do then, we first reset a computation called the loss gradient computation. And so this is something that might be a bit weird right now because we haven't done any implementations of that yet. So this is just something where we reset everything to 0. That's like a best practice in PyTorch. Just, making sure we don't have any baggage from some previous runs, just resetting this. Then we compute the loss on the current batch. So this would be the cross-entropy loss that we've talked about so far in this chapter. And then here, that's the core part where we compute the backward pass to calculate these loss gradients. So the loss gradients were briefly mentioned here. I will also show you where you can read more about loss gradients if that's a new topic in one moment. So, but just to finish this figure, we compute the loss. Based on the loss, we compute the loss gradients. And then using the loss gradients, we update the model weights, the weight parameters. So for example, in previous chapters, we looked at the nn.linear layers, and they have a weight matrix, and n.linear.weight. Or our layer norm also has these parameters, and these are things that can be trained and optimized during the neural network training. And here model weights corresponds to all these parameters, like the layer norm parameters, the QKV matrices in the attention heads, the nn.linear layers, and so forth. And we use the loss gradients to update the weights to optimize the loss, which means minimizing the loss towards 0. And then optionally, we can train some statistics. So for example, the training and validation set losses and some other things to make sure the model is making progress. And then we can also visually generate text, have the model write some output text so that we can read the text and see if this is actually making sense or not, if the model finally learns how to generate human readable text. So this is the brief outline. And I mentioned loss gradients here. And if this is something that is not familiar to you yet, I don't want to go into too much detail in terms of explaining how all this works, because it's like a deep learning topic that would be a good topic for a different type of book. However, I mentioned this before, I have written an introduction to PyTorch here. Actually, this was originally the first chapter. It was like a 40-50 page chapter. But then I thought, well, this book is supposed to be about LLMs and not deep learning, because otherwise, it could be an infinitely long book. So I moved this chapter from chapter 1 to the appendix. But it's actually, I hope, a really nice chapter explaining how deep learning works and PyTorch works in a reasonable time frame, like 40-50 pages. And here, if this is all new to you, like computation graphs, loss gradients, there's actually a nice section here you may want to read through. And so here I'm explaining this with a simpler example with a trainable weight parameter and so forth. And then the target label, for example, in our case, the target token IDs, the computation of the loss, and then how we backpropagate this. So this is a calculus concept. I'm trying to keep it simple here for a simple neural network, because PyTorch takes care of this for us. So PyTorch is doing all this when we call dot backward. So there's a method we will see in a few moments. It's called backward, and it will do all of this. And then we will update the model weights using the gradient. But you don't have to necessarily understand this. So if you are new to calculus and everything, I think it's nice to understand this, but it's not 100% essential. What I think is essential is that we are trying to optimize or update the weights such that the loss gets minimized, which then leads to the model creating more correct tokens, or ideally the target token IDs. So yeah, to show you how this works in code, let me just post the whole thing here, and then we will go through this step by step. So this function here, it's called train model simple. Why am I calling this simple? This is, yeah, I would say a relatively simple training loop, a minimalistic training loop. It does everything we need. And this is also what you can use, for example, to train a convolutional network for image classification or other types of neural networks. But it's relatively minimalistic because there are some other bells and whistles that you can optionally add to this if you want to. And so I've written about this here in Appendix D, where I'm talking about something called like a learning rate scheduler and gradient clipping and so forth. So this is more like, I would say, an advanced concept. So once, I think, if you finish chapter 5, you can optionally look into this. But, you know, it's not 100% essential to understand how pre-training works. So here, this is really like the big picture, the model training. And so what we have here, going through this step by step, is we keep track of certain things. For example, the training losses, validation losses, so we can look at them. Here we also keep track of how many tokens we have processed and how many steps we did, like training steps. And then here, this is the iteration over the epochs. If I go back to the figure I showed you earlier, one moment, here we go. There. So the first here, this first box would correspond to this first for loop. We set the model into training loop because before, when we played around with the model, we had it briefly in this evaluation mode. So it's actually a good practice at the beginning of a training loop to just make sure it's in training mode, which will then enable the correct behavior of dropout and so forth. Here we are now iterating over the training loader, similar to what we have done when we computed the training and validation set losses. Here we are resetting the loss gradients. So we are doing that because later we compute the loss gradients, for example here, and then for the next round, we are resetting it. I could also just, I mean, it depends really, it would do the same thing. If we have never computed them before, it would make no difference if we reset them after or before. So it's just, I think though, a good practice to have it just here in case you played around with the model and you accidentally computed something. So this is just like, a good practice to have it here. We compute the loss, the training set loss. So on the current batch, so we are iterating over the batch, and then we use our calc-loss batch function, which we already implemented in the previous section here. So it's a reusable function. By the way, in the book, in general, I made sure to minimize clutter so that we can reuse functions as much as possible throughout the book. So I think that helps also keeping track of what is happening. And so there are not too many concepts, keeping it as small as possible. But of course, sometimes there's a lot of code because it's necessary, but I'm trying to keep it also a bit minimalistic for readability. And so here we compute the loss, that's the cross-entropy loss. And then we do the backward. And so the backward, so I mentioned before, when we do call the model to create the logits, and the logits are actually created in this function. So where we are here. So here we have the logits that are getting created here in the calc-loss batch function. And I mentioned something like a computation graph before. So when I talked about the no-grad function, where we don't want to have this computation graph. So the reason why I didn't use the no-grad function inside this calc-loss batch is because now we actually do need the computation graph. For evaluating here, we don't need it. But here, down here, we do need this computation graph. So this is computing or creating this computation graph. And maybe one more time here. If I go, where was it? Here. So this computation graph, if we have a computation here, in this case, a very simple computation like this, you can think of it as a simple model. It will create a computation graph like this one here. And in a similar sense, PyTorch will create this computation graph of the model when the data passes through the model. So let me just go through the model here forward. So here, when we call something like, model X or model inputs, this will execute always the forward method. That's just how PyTorch is implemented. So based on what's done in this module, the behavior of a PyTorch module is always, when we pass input, that it goes through the forward method. You can explicitly also write it like this, but it's best practice to do it like this because there's some extra computation happening. But what happens is this gets executed, and this will result in a computation graph for these computations, similar to what you're seeing here. And then PyTorch, when you do backward, it can calculate these gradients here. So this is the computation graph that's created during the forward call. And then you see there's this backward call, which will create this computation graph. Oh, sorry, the gradients from the computation graph. So that's computing the gradients. And then optimizer step. This will use an optimizer, for example, stochastic gradient descent or ADAM, to apply these gradients. So the gradients get multiplied by a learning rate, which is a hyperparameter that says how much we want to update. And then the model weights get updated, basically. So if this is all new to you, it's maybe not a bad idea to go through this introduction to PyTorch and the brief introduction to deep learning. I do have also this whole class on deep learning that might be interesting to you. I have actually multiple classes. So this is very slow right now, but I have multiple classes also. So there we go. If you're interested, this one here or this one here, they both go through the concept of deep learning and explaining this a bit more detailed. But if you are short on time and you want to just get the basics, I think Appendix A is actually a good way to start. So you can read this maybe in a few hours instead of a few weeks or days. So that's like a nice short introduction. So, but yeah, back to our training function here. Then we just increment the tokens we have seen, the global step, how many steps we have taken. And why we need the step here is I'm just using it for optional evaluation. So I'm saying if we have evaluation frequency here that we can set here, for example, every 10th step, if we set it to 10th, every 10th step, it will trigger this code. And in this code, we evaluate the model. So we evaluate the training and validation loss here. We append the training and validation losses to our list just for record keeping, so we can plot that later, and the number of tokens. And then we also just print it out so we can see the progress. And then this is happening for each batch here. And this is happening every 10 batches, essentially. And then every epoch, so here for the outer loop, for every epoch, we are also additionally printing a small sample, like just giving it some sample text and see how the model is doing. So the evaluate function here for completeness, it is similar to what we have used before. So it's similar to this calc loss loader here, except we are using it twice. So we are calling it here once and twice, so to get the training and validation loss. And so we can compare them and see if the model is overfitting. And then this generate and print simple function, it puts the model into the evaluation mode. By the way, here it's also, so to disable dropout and everything. Then we essentially encode some sample text, similar to what we have done at the beginning of this chapter. And then again, similar to the beginning of this chapter, we call the generate text simple function. And then we decode it and put it back into training mode. This might not be strictly necessary because we already have train here, but it never hurts. It would just skip it, but it's not a bad idea sometimes to do it, so in case we forget or something. So yeah, and so this is essentially the training function, and then let's call this training function. So we are initializing a new model. Here we are using the random seed so that you get the same results that I do. So for the initial model weights, here optionally we put the model onto the device. So here personally I'm just running this on a CPU, but you are welcome to run this on, if your computer supports it, on a GPU or the MPS device that I mentioned, if you have a MacBook or Mac Mini or Mac Studio or something like that. However, you might get slightly different results. It will be faster. The results might not be 100% the same, but it's something you can still do. I'm just doing the CPU version here because, just to show you what numbers you would get on a CPU and GPU. Because GPU, based on my experiments, you get the same results as on the CPU. Here we have a Adam optimizer, Adam W. So that is an optimizer, a version of Adam with weight decay. Again, it's like a deep learning concept. I do think I covered it in my lectures. If you are curious, there should be something on Adam somewhere. So, but it's not strictly necessary. You can think of it as a way of computing the gradients and applying the weight updates essentially on the model parameters. And the learning rate is how fast the model learns. So this is instantiating the model and the optimizer, which we pass here, here and here to this train simple function. And we are going to train for 10 epochs. Why 10 epochs? It's just something that happened to work well. So in reality, when you train a real neural network, for example, I don't know, Gemma 3, Llama 3, and so forth, they train these networks on 14, 15 trillion tokens, or DeepSeek version 3, which will cost you a few $1 million and will cost or will take thousands of GPUs and take months of your time. So I assume you don't have millions of dollars and months of time and thousands of GPUs. So we are keeping this example small, train this only on a single book, The Verdict, the short story. And because this short story is so short, one epoch would not be enough to get the model to learn anything useful. So I'm just increasing it to 10 epochs. But, like normally people train models for 1.5 epochs max. Usually it's just one epoch because the data set is like 14 trillion tokens and so forth, trains for months. And so here we just keep it small to make it cheaper, but then we need a few more epochs to see that the model is actually learning. And then, we will have a start context, the familiar every effort moves you, and see if the model can create more comprehensive text compared to what we had before. So I think before it was just generating gibberish, and now we will hopefully see that the model generates better results. I hope this actually runs because I'm actually recording this video also on this MacBook Air, and this is at its max already with the camera and this screen capturing. So I hope this will work. We will see. Of course, the familiar problem. Okay, so let's see. It might take a few minutes. So I remember when I was running it without any recording here on and everything, it took about 4 or 5 minutes, so it's pretty fast. But we'll just wait and see. So we can see now that the model is not generating anything useful, but what we can see at the same time, what is actually good and what we want to see is that the loss is going down. So we can see the training loss and the validation loss, they start off high and they go downwards, which is good. So we want to minimize the loss so that it reaches or it goes towards 0. You can see it's still not doing anything useful. It's generating words, but it's repeating the words, not anything useful yet. And by the way, I don't know if I talked about this before, but the model we are training in general, the pre-training, trains the model to just keep on generating text. So it's also called like a text completion model. And this is true for basically all LLMs. Later on in chapter 7, we will train the LLM to follow instructions. So that's a separate step. It requires a separate approach. So right now we are only pre-training to generate the next word in some text. So if we provided some text, it will just keep on talking, like me at the moment. But yeah, later in chapter 7, we will also learn for the model to how it follows instructions, and it will also then have a stop token to stop generating text. So we can see, yeah, it is already, I would say, getting slightly better. So it's not, at least not repeating the words anymore. So it is generating something. He had the donkey. I mean, it's improving at least. So we see it's getting better if we consider that it first just generated commas and then ands and so forth. Yeah. And we can also see the training loss keeps going down, but the validation loss gets stuck around 6. This is kind of expected because we have a very small data set. And so the model sees the training set multiple times, it starts overfitting. So if we had more data, like I do actually have an example. Let me, in the meantime, while this is training, go here and show you some bonus material. So I do have an example here. I have a lot of bonus material, as you can see. So there's the alternative weight loading, which we will get back to later. I have a pre-training of the model on the whole Project Gutenberg dataset. So Project Gutenberg is a website of public domain books. There are lots of datasets out there, but the copyright debate is still going on, whether it's allowed to train a model on certain data. So here, this is only public domain data, which should be fair to use in the US. So here I have like an example. I think I trained it for 1 or 2 weeks once, and there you don't have that overfitting, of course, because the model sees different texts each time, so the training set doesn't repeat. What I also wanted to mention is, yeah, hyperparameter optimization, if you're interested. This is maybe also nice. We'll not go through this, but this is just adding an interface to the LLM. So you can then type it similar to ChatGPT, and the model responds in a visual interface. So it's just a little add-on here to our model once it's finished training. But yeah, I'm not going through these all because this is optional material. You can explore it maybe afterwards. What is interesting is maybe I actually, just for fun, we coded the GPT architecture in chapter 4, but I also coded the Llama architecture, went through this step by step. And so if you're interested in training a Llama model, Llama 3 model, you can use the same training function. So everything is the same, just a different model. What I wanted to talk about, here. So I also have some bonus material on making the training faster. So I mentioned before, I kept everything very simple, very vanilla. So it runs on any computer. It also runs on a single GPU, but it's not optimized for efficiency. It's just optimized for learning. And here I have some bonus material where I make some changes to the code, and it will make it significantly faster. So you can read through this. There are, I think, 10 tips to make the model much faster. So if you're interested in that, so before I was measuring the speed in terms of tokens per second. Before it was generating 142, was going through 142,000 tokens per second. And then here it's about 4 times faster afterwards. So it's a very big improvement. Well, actually, this is for multi-GPU. Okay, sorry. So of course, multiple GPUs make this 4 times faster, approximately 3 point something times faster. Here's the speed advantage, so 142,000 tokens after the 10 steps. And before it was just doing 12 tokens. So it's like 10 times slower. So I made it basically 10 times faster by applying these tricks. But something like this, it might not work on any, not on every computer, because it has some requirements. For example, also bfloat 16. This should actually work now, I think, on most CPUs. But you can work through this on your own time. This was optimized for GPUs, and bfloat 16 doesn't work on every GPU. I think the GPU has to be an Ampere like A100 or H100 or newer. I think L4 or L40 also works, but older GPUs like what do they call it? Like the T, even forgot the names. The T model GPUs, they won't work anymore here with this bfloat 16. But anyways, it's a topic for a different time. Yeah, I was just trying to pass the time where our model was training here, but I can see it's now finished. So what we can see is the training loss went down, and we have actually a very small training loss, which is nice. Validation loss is high, but can't have everything with a small example data set. So it's a trade-off we make for having something that trains in just 5 minutes instead of 5 months. And yeah, you can see the text kind of makes sense. So what it says is every effort moves you. No, was one of the axioms he laid down across the so and so and so. You might get slightly different results because I may also have changed certain things compared to the book while I was typing this here with the random seed and the data set and so forth, the shuffling. But I think it should, in your case, at least get something that is in the right ballpark here. And then just to wrap up this section, because I know it was a very long section, I was talking a lot here. I wanted to just also add a plotting function. So this is just a matplotlib plotting function that will plot the number of epochs, the training losses, and then just visualize what we are looking at here in this text. So let's see how that looks like. And by the way, this is why I was keeping track of everything here and here, especially the lists, because I'm returning them here at the bottom here. Training losses, validation losses, track token scenes. So I'm returning them from the list here. So we save them here so that I can visualize them here in matplotlib. And yeah, we can see the training goes down towards 0 like we want. Validation, it's struggling a bit, it's going down, and then it's getting stuck. So it means that the model is overfitting. But again, it's because we have a very small data set for educational purposes here, just so that it doesn't take too long. But this is something you can also apply to a larger data set, of course. Okay, I think this is it for this section. In the next section, we will talk a bit more about the sampling, because so far we only used a very simple sampling procedure, and I will explain some alternative ways we can implement to generate text. So now I want to talk a little bit about decoding strategies or text generation strategies to control the randomness. And so here in the previous section, we've seen that the model starts overfitting to the training set. And by design, models, it's essentially at some point will learn how to generate the next token as it appears in the training set. So memorizing. And in practice, no matter what LLM you use, whether it's through ChatGPT or other providers, usually they implement a sampling strategy that uses either top K or top P sampling and a temperature scaling. And I wanted to talk a bit about that and how that works. So before, what we did is we implemented this generate text simple function, or we used the generate text simple function, which we have here in chapter 4. So in chapter 4, we implemented generate text simple. And here what we did is we always grabbed the token with the highest probability. So, and if the model is well trained, this will ideally correspond to the target token ID. So that is what we want during the training. The model needs to have a reference for learning. So we want the model to learn how to generate these target token IDs. But then when we use this exact method, it will exactly try to memorize the training data. So let me actually see something. So if you look here at the generated texts, I'm pretty sure if we take some of the text and go into the verdict and just search for it, we can see that these actually occur in the training set. So this was actually non-planned. I just did this spontaneously, and I'm glad this worked out. So we can see some of the words or phrases that it uses in that specific order, they come directly from the training set. And that is just due to overfitting or just memorizing the training set. And that's just like an artifact or a side effect depending on, or it's a side effect of the training essentially, because we want the model to generate the target token IDs. But then during inference, we don't always want the model to memorize, right? So we want the model to be a bit more creative. And so in this, in the following videos or sections, I will explain techniques that we can use to make the model more creative. And like I mentioned before, most LLM providers are using these techniques under the hood. It's just not visible to the user. But yeah, to start, because it has been a while, just to show you again what we have. So we have trained the model. I would say let's just move it to the CPU to make things simpler. You can keep working on the GPU, but for simplicity, let's just move things back to the CPU, put the model into evaluation mode to disable dropout and everything. And then we will use the generate text simple function on the model, and we will use our familiar, start context, generate 25 tokens, and look at the output. And so this is something that we will use now as a reference. And then I will show you in the upcoming sections how we can improve this to improve the creativity of our model. So we will be now implementing different techniques to control the randomness in our text generation. So one of these techniques is called temperature scaling. So in this section, I will conceptually explain how a temperature scaling works. And then in the next section, we will introduce another technique called top K sampling, and we will see we can actually combine those techniques. And once we have both techniques, we will actually go back and modify the generate text function. But for now, just to make sure we understand how temperature scaling works, I wanted to work with a smaller example. So for that, I prepared a smaller vocabulary where we only have 9 tokens. Before, we worked with a vocabulary of 50,257 tokens, which is a bit hard to track if we want to print out results and look at plots. So for this example, we are looking at this small vocabulary. And I will also create the inverse vocabulary similar to chapter 2 so that we can map backwards from tokens to words. So it's essentially just the same thing flipped. I also prepared some sample logits. So these logits would technically be created by the model by calling the model on the inputs, but yeah, to keep things a bit smaller, self-contained, and easier to follow, I just took the liberty and made up some values here. They would, in theory, be generated by a model, by passing inputs to the model. But I want to keep things simple here. And we can see there are different values. And we can see there are medium-sized values, very large values, very small values, and so forth. And we could technically work with these logits directly, but we will apply the softmax function to convert them into probabilities. Let me just, before I stumble upon my keyboard here, copy this. So here we have the probabilities from the softmax, similar to what we have done before, given these logits. And we can see these are like now the probability values associated with these logits. So we see this is a very small value. So E minus O2 means 0.06. And then here we have a pretty large one. This is 0.57. And here we have 0.35, very small value, 0.00013, and so forth. So there are different probabilities for each of these tokens. And if you recall, the way we used or we sampled, for example, if I do next token ID, the way we sampled, we used the argmax, and we used the argmax on the probus. Let me just return this as an item. If I do this, this should give me the probability or the position where the highest probability is located. So 3, I can count 0, 1, 2, 3. Makes sense. This is the largest value here. This is 0.57, a 57% probability. And token number 3, I can actually look this up maybe in the inverse vocabulary. So next token ID. Oops. Somehow pressed the wrong button here. There we go. It's forward. So forward token ID 3 is the next generated token that the model would generate with our generate text simple function. And yeah, and so that is deterministic. No matter how many times we execute this argmax, this is always the highest probability. This will always be selected as the next token that is generated by the model. Now, what we can do is there is something called torch multinomial. And torch multinomial lets us sample from these probabilities here. So instead of deterministically always getting the largest token, we will now get the token proportional to these lodges or proportional to the probability values. So this means if we do it like this, 57% of the time this token gets sampled, and 35% this token gets sampled. And then 0.001% of the time this token gets sampled. So to show you what I mean, I can execute this and it gives us forward because yeah, it's the most likely token. So most likely this will be returned. If I disable the random seed for a moment, if I execute this again, I see forward is returned again. Let me do it one more time. Now I can see actually a different token is returned toward. So toward it's token number 7 corresponding to 0, 1, 2, 3, 4, 5, 6, 7 to this one here. So occasionally it will generate toward and occasionally it will generate forward because it's proportional to these probabilities. So now we added a bit more creativity or randomness to our model. And it is not totally random, right? Because it's still depending on these probabilities, and these probabilities get learned from the training data. So the model, how it learns, it's learning to generate the next token in a given text, where the given text is the training data. And there could be different combinations of words occurring. There could be a sentence that says every effort moves you toward your goal or moves you toward something. And there could be a sentence, every effort moves you forward. It could be a sentence itself. And so depending on how frequently these word combinations occur, the model will learn these probabilities. And some of the time, or some tokens are more likely in certain positions than others. So it's still just statistics. It will just, be based on the frequency things occur in the training data, essentially. But at the same time, we don't brute force always return the most likely token. We sometimes also add, or we have this little freedom here to sample from all the tokens. But we make sure that the model doesn't generate nonsense by weighing them or having a weight that depends on the training data statistics. Because if we would do it totally randomly without weighing these probabilities, then the model will again generate gibberish where all the tokens are equally likely. So we have this kind of like common sense based on the training data that more likely tokens will be more likely sampled. And so this is one way we can generate these more, I would say, creative texts, or not just memorizing from the training data. By the way, instead of just brute forcing here, executing this, I can also, I have a more sophisticated function here. I can also just repeat this 1,000 times. So what I'm showing you here is a function where I call this torch multinomial 1,000 times, and I just save the results, look at the frequencies, and then just print them out. And so you can see 582 times out of 1,000 it prints forward, 73 times closer, and 343 times toward, and even 2 times inches. So yeah, so you can see it is not always generating the same tokens, and we can further influence this. So this is just based on the probabilities, but there's a common technique called temperature scaling where we modify this distribution further. So I will make a function called softmax with temperature where I will apply this temperature scaling to change this distribution a bit. So how it works is what you're looking at here for now is nothing new. This will be like the regular softmax. So we have the logits Then we have the scaled logits, where I'm just dividing the logits by a number. Here it's a 1. And so if we divide a number by 1, nothing happens, right? 5 divided by 1 is still 5. Or 0.5 divided by 1 is still 0.5. And so here, nothing new happens. So we just apply the softmax like we did before. But now if I replace this one by a different number, I call this the temperature, I influence the values of the logits. I make them either smaller or larger, and that will then affect the softmax. So this is helping us kind of as a hyperparameter, the temperature, to change the distribution here. So I, as an example, I can consider, let me execute this. For example, the temperatures 1, 0.1, and 5. So here 1 will not do anything. This is like I showed you before. It will just divide by 1 and nothing happens. 0.1 will make the logits larger, right? So it will, so for example, if I have 10 divided by 0.1, it will be 100, right? Oops. So we'll make the logits larger, or we divide them and make them smaller, right? So by that calculation here, we are influencing the logits, and then we will get different softmax values. So smaller values here, they will essentially result in larger peaks, right? Because we make the logits larger, and the larger the logits, the larger the softmax values. And if we divide by a larger number, we make the logits smaller, which will make the softmax also smaller. It will distribute the softmax more. Because in the softmax function, remember, we have the constraint that they still sum up to 1. So if I go back here, and I type probas.sum, you will see they sum up to 1. And it will be still true here, because everything that comes out of the softmax, I mean, by nature, by design, by this function, will sum up to 1. So if we make some values larger, the other ones will be correspondingly smaller. So let me show you actually in a visual how this will look like. So if we have these temperatures and we compute the softmax here, so what I'm doing is I'm applying this function to the logits we had, to the logits up here, right? So I'm applying this with a different temperature for these 3 temperatures. And then we get these scaled probas. So let me just show you the shape of this. So this is 3 scaled proba values. Oops. It's a list actually, sorry. So we have 3 probability tensors, where the first one should be corresponding to our original probas, because we haven't modified anything. It's just dividing by 1. But then when we have this one, oops, this is with a temperature of 0.1, and we have this one, we can see these are different. Now these are kind of closer to each other, and these are more peaked. You can see some of them are very small and some of them are very large. So this is a 99%. So I actually prepared also a plot so we can look at this more visually. So this one is just plotting these out as a bar plot here, and you can see on the y-axis the probability values you saw here, and then for a temperature of 1, which is the original probability values, you can see we get about 57% of the time we get forward, we get 35% of the time toward, and then with a smaller probability closer. But now if we make the temperature smaller, 0.1, this will be a more spiked distribution. You can see these large peaks here. At forward, it's 99%, and a small one at toward. So if we go here, we have 0.09% for toward and 99% for forward. Now, if we make the temperature larger, we make them 5, you can see the distribution becomes more uniform. So the values are more closer together, because each of them, they still sum up to 1. So that's one constraint, right? So if we make some values larger, some other values have to become smaller, right? So that's like the constraint we have. And yeah, with that, we implemented temperature scaling here. And this is one technique we can further control these values, how often each of them gets sampled. So next we are going to implement a sampling technique called top case sampling. So here we are not going to implement all the possible sampling techniques because yeah, that would be a book by itself. So I was only focusing on a few popular ones that give you the intuition of how sampling works, like the temperature sampling and the top case sampling, and they are also both relatively frequently used in LLM applications. There's another technique that is very popular, for example, top P sampling. It's not going to be covered, but yeah, I briefly discussed it in my other book, the Machine Learning Q&AI book. But top case sampling is yeah a nice technique that we can combine with a temperature sampling, as I will show you in the next section. But by itself, let's briefly discuss what temperature sampling means. So I should have a nice figure here somewhere, I hope, in section 5.3.2. So here, that's the illustration of top case sampling in a figure. So if we have, again, our small vocabulary just consisting of 9 tokens with the index position shown below the token strings. So suppose we have the logits. These are the next token logits we worked with previously in the previous section. And now top K sampling selects the top K largest logits. It's quite intuitive, like the name says, top K. What are the top K highest logits? And here, for example, if we set K to 3, it will focus on the 3 most likely tokens or logits. So on the 0, the 3, and the 7 in this case. And what we will do is kind of similar to what we have done when we created the causal mask. So we will replace all the values we are not interested in by -infinity. And then we will apply the softmax. And what the softmax will do is it will rescale this. So again, that everything sums up to 1, but the -inf gets replaced by a 0. This is similar to what we have done in the causal mask. But now we are applying this here to the logits and for the token generation. And yeah, and why is this useful? So the reason why it's useful is in this case, we can make sure that the LLM will never generate, even with low probability, it will never generate any tokens that are not the top K token. So it helps a bit minimizing like the chance that LLM generates complete nonsense because we completely eliminate unlikely tokens. But then also, of course, it limits a bit the creativity of the LLM. It's kind of like a trade-off. 3 is just an arbitrary example. It's a hyperparameter. In reality, might set that to 50 or to 100, 500, because in reality, we are working with larger vocabulary. Here we only have 9 tokens, and our real vocabulary is 50,257. But yeah, let's just see this in action, how this actually works. So let me just copy the next token probabilities or logits that we had here. We just redefine them so we have them here to look at. And then what we can do is we can define top K as 3 to mimic what we have seen in the figure. And then there is actually a PyTorch function. It's called top K. And for that, we can provide the next token logits and then the top K, how many we want. And so this will return 2 things. So this will return here the top logits. So the highest logits found here. So this would be 6.75, 6.28, and 4.5 here. So you can see it's also sorted by magnitude, which is quite nice. It's convenient. So let's give that names. Let's give it top logits and top position as the variable names. And yeah, so it's already sorting them for us. I can maybe just print them again here. So we have them. The next thing is now we want to set everything else to -infinity, right? So we have the next token logits. Oops. here. And what we want to do is we want to keep this one, and this one, and set everything else to -infinity. So there are multiple ways we can do that. One way is, if we create these new logits with the -infinity values, is to use the torch.where function. So how does this work? So this accepts a condition. And so for the condition, we can say, for example, everywhere where the token logits are smaller, what's nice is actually this is sorted, where they are smaller than the smallest of these top logits. So what I'm saying here is, if we look at -1, this should be the lowest one, right? So this is the lowest one in here. And we say everywhere where this is true. So here, everywhere where we have a logit that is smaller than this value, we have this condition true. And then what we do is we define an input and say everywhere where this is true, we say tensor float -inf. And otherwise we say just we keep the original value. Okay, so here we can't just say something like 1 or a torch tensor 1, because then everything will be either -infinity or 1. Here we provide the input token logits again, so it can take what it needs from that tensor. So again, so what we are doing is we are replacing the true values with input, and input in this case is -infinity. So these will get replaced with -infinity, and the false values will be replaced by whatever is found in the original tensor. So let's actually see if that works. I forgot a comma somewhere here. And yeah, so what we have now, let me clean this up. What we have now is our new logits, where we have the highest top 3 logits kept here, and then the -infinity. And yeah, remember how we used the softmax to now apply this to the logits when we created the causal mask. We can do the same thing here. And since we only have one dimension, this will create this new tensor. And here, yeah, we can now have the probabilities here in a rescaled fashion, where we have 57% for the 0, 1, 2, 3 for the third position, and so forth. So here, this is one way we can zero out other probabilities. It's kind of related to what we are seeing here with the temperature scaling, where some of them get a higher probability when we set the temperature to a smaller value. But here we are more explicitly controlling how many tokens we want to keep or consider when we sample the next token. Okay, so now we have introduced 2 topics, temperature scaling and top K sampling. And so in the next section, I want to actually combine those to update our generate text simple function that we implemented earlier in this chapter. So in the previous 2 sections, we introduced 2 different sampling techniques, the temperature scaling and the top K sampling. Now we are going to combine those 2 to update our generate text simple function that we used earlier in chapter 5 to generate the next token. So let's go to our previous chapters.py file. And here we have this generate text simple function, which we originally implemented in chapter 4. And we are going to modify it step by step for temperature scaling and top K sampling. So right now it's just doing the greedy sampling, always generating the most likely token. But yeah, we want to add some randomness and sampling to it. So let me copy this here first, and then I will modify it step by step. So let me also get rid of some of the text here, because then we can fit more code into this window. Then it's easier to read and see what's going on. And so one thing I'm going to do first is I'm adding a few arguments here. I will add, let's say, the temperature. And we can't divide a number by 0. So this, if we have logits divided by temperature and the temperature is 0, this will fail. But I will add a if condition in a few moments. So the temperature scaling gets skipped if the temperature is 0, so that the 0 allows us to say basically we don't want to randomly sample. Then let's do top k, and we can also set a default parameter. Let's do none. And one more thing I want to introduce right now is the end of sequence ID token. So we are not really needing it right now. This will be a concept, end of sequence token, that we will be revisiting in chapter 7. So in chapter 7, we are going to instruction fine-tune the LLM to give us answers to certain questions. And then part of this procedure is also teaching the LLM when to stop generating the answer. And for that, we will be using the end of sequence token ID. And as I mentioned before, I kept this book relatively efficient. So we are going to reuse this generate text simple, or the new generate text simple function, later in chapter 7. So I'm already adding it here so that we don't have to redefine it later. And just to briefly explain what I mean by end of sequence token. So EOS stands for end of sequence. So if we have the tokenizer, it has a certain vocab size, in our case 50,257. And the last token here in this particular tokenizer is the end of sequence token. So we can double check this, and I can do, because Python has 0 indexing, so I'm going back by 1 position, so I can also just type 6. So this should give me this end of text token. So this one corresponds to this, or we can use this as the end of sequence token to tell the LLM or our generate function when to stop generating text. So what we could do is, for example, we can say if end of sequence ID, or you can maybe do it like this, it's more intuitive. If our next token equals the end of sequence token ID, then we break, so we don't generate more tokens. And why is that useful? For example, there might be a question, I mean, we have the max new tokens, but there might be a question that only requires a shorter answer than we have defined in max new tokens, so we save space. So for example, trivial example, we ask our LLM to answer the question, what is 2 plus 2? The answer is 4. So even if we have 25 tokens, we don't need 24 more tokens to answer the question. We can just, stop generating after this short answer. And so using an end of sequence token ID and teaching the LLM when to use it, we can get shorter answer and save time and money in that sense. So this is just something we will be revisiting later in chapter 7, but I will just have it here already. So for reuse. And so let me now add temperature. Maybe let's do top k first. So we say if top k is not none, then do something. And then we can also do, let me just have some placeholder code. If temperature is greater than 0, then do something. And else do, one of these days I will get used to this keyboard here. It's slightly different from the position that I'm used to, so I'm always making these typos here. So what we have here is we use top k sampling if we have a value, for example, 2, 3, 4, 5, 6. We use temperature scaling if the temperature is greater than 0. And otherwise we use our procedure as we have used it before. So let's fill in the blanks. Let's do the top k maybe first. So we can copy the code from the previous section. Can just fill this in here. I see I have to make one modifications because the last or the next token logits are now just called logits. So we'll have to make sure this uses the same variable name. And then here, this one. We'll copy this one here. Okay, and the same thing, we have to make sure we use the same variable names here. Okay, and I think because there's one more dimension, we also have to make sure we get this correct here. This looks okay to me. Okay, we are not doing any softmax because we're going to use the softmax here in the temperature scaling, because the way the function is set up, if the temperature is 0, there is no randomness, there will be an argmax. So we don't need to do anything here. We will take care of this in the temperature scaling scope. So let's apply the temperature scaling. And then we need, of course, the torch.softmax to get the probabilities. What else? Yeah, and then we need the multinomial, right? Multinomial, and we give it the probabilities. And I think we only want one sample, not many samples. So I think if I see it correctly, this should work. So what we do is we do the temperature scaling if the temperature is greater than 0, and then also if there's a top case scaling happening, that is also used, because this will do the minus infinity, and then we do the temperature scaling. If the temperature is 0 though, then it will use torch argmax, so it will be deterministic. So what that means is, by default, it will behave similar to what we had before. So let me maybe just see where we had, or I can just define it below here. So I wanted to just show you the default behavior. Let's actually rename this, because it's not the simple text generation function anymore. It's slightly more sophisticated so that we can tell them apart. And then let me actually just copy it from here. Let me show you how it works. So let me comment this maybe out for now. And so this should work similar to what we had before if we use the default for top K, which is none, and the temperature of 0.0, because then this code won't get executed, and then it will behave similar to what we had before. So this should be, yeah, deterministic behavior. And then if we add the top K and temperature scaling, we get a different response. So here, this is essentially now combining our sampling strategies, but as you might see, this is still not really making sense at all. This is just some gobbledygook, so it's gibberish almost. I mean, there are words that make some sense. So to work on surprise, us had gone with random. It's relatively random still. And this is not because our function here is bad. It's really that we have not trained the model much. You know, like that little training on that one little book, it doesn't do that much really if we ask it sometimes questions. So don't worry about it yet. We don't really want to spend thousands of dollars on training. We will be actually at the end of the chapter load the pre-trained weights from OpenAI. And then later in chapter 6 and 7, we will do actually more training that does actually something useful. But for the base model, for the pre-trained model, yeah, you can't expect much from training for 5 minutes on some simple text. So for that, don't worry about it. We will be loading pre-trained weights into our architecture so that we have a solid model to work on in chapter 6 and 7. But yeah, we will be reusing this function, because I will show you once we have good model weights, this function will actually work quite well. And yeah, and so by the way, how did I determine these numbers? I just put in some numbers, but in reality, when you use the model usually comes with a model card where the developers of the model, they suggest some settings for top K, top P, and temperature scaling. So if you follow the new models like Llama and everything, they do come with suggestions, and it's usually a good idea to use these suggestions. But now that you know what temperature scaling means and how it works, you know that you can actually increase the temperature to increase the randomness and decrease the temperature to reduce the randomness. And that was, this was mainly the goal here in this lecture, to explain a bit what these methods do. And once we have a better model, once we have loaded the pre-trained model, let's actually revisit this and play around with this and see what we can generate with slightly better model weights. So let's now see how we can load and save our model. I promised you later on we will be loading the pre-trained weights from OpenAI, but it is not a bad idea to learn how we can save and load our own model, just in case you want to revisit this without having to retrain the model. It's just like it's a nice thing to know how we can save PyTorch models. So in PyTorch, the recommended way is to use the so-called state dict of a model that we save, and this contains the model weights, like the weight parameters of the token embedding layers, the query weights, also even our mask here, our causal mask, which we saved as a buffer. So it contains all these things, but it doesn't contain information about the model architecture. We will get to that in a few moments. And then we can use the torch save function, and we can give it some name. Let me just call that model.pth. It's just like a common convention for PyTorch files to append pth, but it can be anything. You can name it ABC, or you can just omit it in general. So it doesn't really matter how you name it. It's really up to you. And yeah, this is how we save a model in PyTorch. Then it should be saved locally to this where this notebook is located. You can also be a bit more precise and add a specific path and so forth. But here, let's just save it relative to this notebook. And then I wanted to show you, more importantly, how we can load this. Let's just add a new or create a new notebook here where we don't have anything. So in order to load this model, because it doesn't have any architecture information, what we actually do need is the architecture. So we had it in our previous chapters.py file. And so we can import our model here, our configuration, and then we can load a new model. So we can do GPT model and then GPT, config. So this will create a new model, and it will have random weights, but we don't care about the random weights. They can be anything for now because we will be overwriting these weights. So we will be overwriting them with our weights that we have saved in this model.pth file. So one more thing, I wanted to define also the device again. So this is what we have used before when we had the CUDA and the CPU device. And now the reason is because we can do a torch.load, and then we type the name of the model file, pth in this case, and then we can say a map location device. So it will load that on a device that we specify. So if we, for example, saved the model on a GPU, but my computer now that I'm using, maybe a week later, only has a CPU, this won't crash because this will then determine, oh, my model only, or my computer only has a CPU, so it will only load it on a CPU. You can also just, overwrite this manually. So here you can just control independently how the model was saved, where the model is loaded. And then, and then we do, so this is, by the way, so this is loading the model weights. So maybe let me execute this in a new cell. I should, of course, import torch. So this is loading the model weights, and you can see this is basically the state dict that we have saved. Now we have to get that state dict into our model. So for that we use model.load state dict, and then we can just copy and paste it in here. And then, it hopefully shows success. And this basically means that we have loaded our model, and this should be then ready to use. So then, we can use it similar to what we have done in the previous sections. So we arrived in the last section of this chapter where we will be loading the pre-trained weights from OpenAI. So the pre-trained GPT-2 weights, which are much better than our own weights because we only trained the model for 5 minutes. But of course, training this whole model on many tokens would of course be very expensive. So luckily, OpenAI shared their weights on the internet that we can download and load the weights. I wanted to also show you in this repository again. If you are interested, you can toy around with some of the bonus material to train a better model than we have done in this chapter. So for example, I have this training on the whole Project Gutenberg dataset. Additionally, you maybe also want to make it faster by applying these tips. So these tips are not applied to this one yet. This is really just the code that we have used in this chapter. So there are more advanced things if you are interested. But just to work with what we had so far, continuing, we will load the weights. You might have actually, depending on your computer, if you are using a work computer, I heard from some readers that they don't allow downloads, so that might be a bit tricky. Some work computers only allow downloads from Hugging Face, but not from OpenAI, and there are different restrictions. So yeah, you might have different problems. In this case, maybe you can post the problem in the forum or on the GitHub discussion board. There are maybe some other readers that might be having the same issue that have solved it and can give some advice, or I also can forward some advice I've seen from other readers. But one more thing I wanted to mention is I also have this alternative weight loading from Hugging Face transformers, or also safe tensors files. So these are two notebooks that do something equivalent to what we are doing here. So if what we are doing here doesn't work for you, yeah, I recommend in chapter 5 on GitHub to check out one of these two notebooks. Which one doesn't matter, both work. They're just two different ways to load the weights from a different place that also doesn't require TensorFlow. So yeah, but to show you what the original way is to load the weights, the official weights. So for that we will use TensorFlow, and we use also a software library called TQDM. It's just a progress bar library. You can install it with pip install TQDM if you have not installed it yet. So I'm just showing you the version numbers that I was using. And so what I'm doing is I'm going to import some code because this code was too much for the chapter itself because of page limits. But then at the same time, I also thought maybe the URL will change in the future. So in the book itself, the code will show you how to download this file from my GitHub repository. But here I'm just doing it manually so you can see where it is. So if you go to the chapter 1 code, GPT download, and it's actually not a bad idea to also, just make sure there's nothing weird on there, because when you download code from the internet, you never know what's in there. So it's never a bad idea to just scroll through this, make sure this looks okay. It's not, I can assure you my code is fine, but I'm just saying in general, if you're downloading code from the internet, it's never a bad idea to, by default, check out what the code actually is doing. So what I will do is I will make a new Python file. I will paste this here, and I will name this Python file download and load GPT-2. Okay, that's what I have here. Just saving this. And then I should be able to import this. No, what happened? No module. Oh, I see. Let me double check if it's actually called GPT download. Sorry, I made a mistake. So this should have the name download, GPT download. So this should work now. Okay, so we are loading this function, which will download the weights from OpenAI. So it's a lot of code. It's not very interesting code, but there are different model sizes. There's 124 million. That's the small model we implemented, and the larger sizes. And it will by default download it from OpenAI. And sometimes the server has some hiccups. So there's also an alternative backblaze link where I uploaded the weights just as a backup in case this fails. And yeah, and this is essentially just downloading the file, printing some progress, and then loading the file contents here and then returning them. So there's nothing really super interesting. You can read through this if you want. This is just like basic converting this from TensorFlow and loading this. But yeah, it's just like a way we have to load the weight parameters. And so what I'm going to do here is I'm loading or downloading the 124 million parameter model, and I will save it to a subfolder called GPT-2. So here we'll be showing you a progress bar. This is why what did I do here? Why I had this TQDM library, so you can see what the progress is. It might take a bit. It's 500 megabytes depending on your internet connection. And like I said, if this doesn't work for you, there are these alternative ways to download this from the Hugging Face hub that doesn't use TensorFlow, and it's just a different URL in case your work laptop doesn't allow downloading from the OpenAI OpenAI folder or library here. Sorry, a link server, however you want to call it. Okay, so let's wait until this is downloaded, and then I will print the settings that we just have here. So the settings, they will look similar to what we had. So the vocabulary size, the context length, the embedding dimension, the number of heads, and the number of layers. And then we will also briefly look at the params. So the params, they save the weight parameters. Here I'm only printing out the keys because otherwise it will be too cluttered. So these are just the keys. So we could take a look at one of those. So for example, WTA, that's the weight matrix for the token embeddings. So if I print the contents here, we see it's a weight matrix, and it has the dimensions 50,257 times 768. So this is similar to what we had in our GPT model right here, right? Token embeddings, the vocabulary size 50,257 and then 768. Our task will now be to load these parameters, all the weight parameters, into this architecture. So this has all the information, the numbers and everything. We just have to make sure we match those. And I mentioned before, there are the different sizes here. I think I should have a figure on this somewhere. Let me see. Scrolling down here. Yeah. So just to explain how they are different. So the sizes, of course, refer to the number of parameters in this model. So there are 124 million parameters, 355 million parameters, and so forth. I think I had a section on how to calculate those. I think it was section, I forgot the section name, but it was in chapter 4 somewhere. The difference between those, how the architectures are different, is they use the same building blocks, but the number of times this transformer block is repeated is different. So we have 12, 24, 36, or 48 times in the different models, how often this transformer block gets repeated. And then also the number of heads in multi-head dimension differs. So you can see here the different numbers. And then also the embedding sizes of the positional embedding layer and the token embedding layer, they're different for the different models. So ultimately, though, we can use the same code. We just have to make some smaller adjustments. So let me copy, I've prepared those here. Let me copy the base configurations, what I've just shown you here as the small model, the medium model, the large, and the XL model. And then we already have our config file, right? So we had our config file here at the top of the notebook. I can maybe just copy it down here so that it is easier to read. And so what we can do is we can take this as our base configuration because it has some other settings, and then we update them depending on what model we choose. So for example, I'm going to copy some code here so then I don't have to retype everything because it's not super interesting. But let's say we choose the small model, the 124 million model. What we can do is we can make a new configuration file where we copy the settings that we had before. And then we update this dictionary that we just copied with the new settings. So the new settings, just to let me just when I execute this, this will take a while. So let me just wait. So we updated with these settings, for example, here. In this case, we already have these settings, so 768, 12, and 12. This is already correct, so nothing happens. But if we change it, for example, like this, we will do that actually in chapter 7, then we will have different settings here, and these will be updating our config file. Now, one more thing we will update is, so the context length, we have a very small context length of 256. We can update this to the original size, 1024. We actually have to because of the positional embedding layer. And the other one is the QKV bias. So I mentioned before, where was I here? It should be somewhere in the transformer block. And then, oh, sorry, I think I need to go back to chapter 3 to show you. Somewhere here. So we have these query, key, and value weight matrices, and we have this linear layer, and then there's usually a bias vector. It's standard in deep neural networks as for the layers, but here we only care about simple matrix multiplication, so we set this by default false. So this is just a simple matrix multiplication, but for some reason OpenAI, they used a bias here. It's very uncommon. No other LLM nowadays does have a bias here. So the bias is it's not like a like a human bias. It is a vector basically. But OpenAI for some reason set this to true. I'm not aware of any other LLM that does that. It's not necessary really. But if we want to load the weights from OpenAI and have the model behave correctly, we do have to enable this. Otherwise, the model will not calculate the correct numbers because it's expecting that this bias is there and then the bias is not there, so all the numbers will be shifted and so forth. So we do have to match the settings that they used if we want to load the original weights. So yeah, that's why I'm configuring it like this. And so this now instantiated the model with random weights for now. So we have not loaded the weights yet, except that we have them sitting in this params here. We have now still the model with the random weights. And now the next task will be loading the weights from params into our GPT model architecture. And this is a bit tricky. It took me maybe half a day, or not half a day, but many hours to figure it out because I had sometimes mismatches and stuff like that. So I have a little utility function that converts the values here from the TensorFlow format into a torch parameter. And then, so it becomes trainable, and then it will also complain if the shape doesn't match. So left and right shape, one of them will be our model weight and one will be the parameter weight, and we want to try to match them up. It's a bit of a tedious task, and I have actually I said TensorFlow. I think this is actually NumPy. I can actually double check. Yeah, I converted it to I think these are NumPy arrays now. There's only just one step here where it is TensorFlow, and then I think it becomes NumPy. It doesn't really matter though. The fact is that we are converting this to TensorFlow, to PyTorch. And for that, I have written this function, which took me a long time back then to write. I mean, a few hours at least. And so what I'm doing is I'm passing here this GPT model, here in GPT. And then we have, so I actually use the short name because otherwise these will be very cluttered. And then the params that we have up here. Now we're trying to load them into our model. And so what I'm doing is I'm iterating over these blocks. So I mentioned before when you print out the results, where was it? Here. So you have the blocks. So these are the transformer blocks in the dictionary, in the parameters dictionary. B stands for the bias units, I think. G, I think, is one of the scale parameters of the layer norm. Word positional embedding. So I think, sorry, this is both the shift parameter of the layer norm and the scale parameter of the layer norm. We will see in a few moments. I can actually double check. The word positional embedding and the word token embedding. And then here are the transformer blocks. And so I'm iterating over the transformer blocks here, and then I do the split. And that is because they have one weight matrix for the Q, K, and V. So they have this merged QKV matrix. I think I went over this in chapter 3 at some point, where I showed you the different attention mechanisms. And I showed you that there are different ways to implement it, and we implemented it like this, where we had separate keys, separate query, key, and value matrices. One other way would be to implement it with a combined matrix, the combined QKV matrix. And that's what they have done, but we want to load this into our into our separate weight matrices. So what we are doing here is we are splitting where was I again? Yeah, splitting this weight matrix into individual matrices, and then we assign them correspondingly. So for the query weight of the bth transformer block, we assign correspondingly this QW and transpose it. So that was also something I had to figure out whether to transpose or not. So here we are just assigning. So I did it like this, so it's not too long, but yeah, maybe it's more readable like this. But you can see what we have here. We have our own model and then this QW from the iteration. Maybe let me go back. Oh, sorry. And so, yeah, we're assigning the weights one by one for the query, the key, and the value. And this is using this thing here where it complains if it's not correctly assigned, and we'll use torch parameter to make it trainable. So yeah, that is what is happening. And then we do the same thing for the bias units. So that's analogous to the weights. Then we do the output projection layer, feed forward layers and everything. Here we have the layer norm, one of the layer norms, another layer norm. And yeah, the G is for the scaling, like I mentioned, and the B is for the shift. And then this is the B and G is for the final layer norm. And then we also have the output layer. And here it comes back to what I described in one of the earlier sections, I forgot which one, where I mentioned that they are using weight sharing, where the input layer and the output layer, so the input token embedding layer and the output layer have the same weight matrix. So that's what I'm doing here. I'm using the token embedding layer also for the output layer. So this, I think I explained this in more detail in one of the previous videos, because I feel like this is already going to be another long video or long section. I won't go over it again, but yeah, I should have covered it somewhere, and I will probably add a comment about this. So long story short, you don't really have to understand all the nitty-gritty details. The one big takeaway is that we are loading the parameter values here into our GPT model architecture. So let's execute this, and this will load it, and then we put it on the device that is supported, for example, our CPU or GPU. And then finally, we can actually reuse our generate function that we have implemented in the previous section and see whether our LLM now generates better results. So let's see if everything works. So we can see now it says every effort moves you toward finding an ideal new way to practice something. What makes us want to be on top of that? So I would say this is actually pretty good text. So this makes sense based on what I can tell as a non-native speaker. This is also grammatically correct. So I think the OpenAI model that we loaded into our model is doing a good job. The weights are, of course, better because we only trained our model for 5 minutes. They trained this for many weeks or months even. So they did a pretty good job. This model works. And also still keep in mind, this is the smallest model. So we used the smallest model. If you are using this model, or this model, you will also again see that the model becomes more capable the larger the model is. So yeah, we learned in this chapter how conceptually the pre-training works. We learned about sampling, and we loaded the pre-trained weights. And in the upcoming chapters, we will fine-tune this model to give it different capabilities from classification to instruction following.